Hi, this is Kevin Trainer. Welcome to part 2 of the lecture on chapter 5 from the Python book by John Zelle, second edition. Chapter 5 is called Sequences, Strings, Lists, and Files. And where we left off, we had just really finishing up the lecture associated with page 137 in the text. And slides wise, let's see. Let's pop the slides up. We're on slide 44. Okay? So I just did a demonstration of the encoding program called text to numbers and the decoding. So let's do that again, just for grins. Okay, so I'm going to run the example code from the book called text to numbers, and it asks me for please enter a message to encode, and I'm going to type Mary had a little lamb. Don't you know? Don't ya know? Okay? And I'm going to press enter. And we get back the encoded string. You'll remember that these have been encoded into Unicode code points. And these are decimal values. You can express Unicode code points as either hexadecimal values, which look a little odd to the uninitiated, or decimal values, which is pretty much the way we do it in Python. But if you go to look them up in a Unicode code point chart, you might see that there are two values for each of the characters. And the one you want is the decimal value. And so we've created a list of these decimal values, one for each character, separated by a space. And now I'm going to copy that. I'm going to go over to the decoding program called numbers to text, and I'm going to run that. And it asks me to please enter the Unicode encoded message. And I need to do, on my Mac, I need to do a Command V because my paste doesn't work down there in the console for some reason. And I'm going to press enter. And there's our message. Mary had a little lamb, don't you know? Pretty nice. Okay. And just to review what was done in this decoding program, we got a string into the variable inString, which had the string of numbers separated by spaces. Then we went down in the beginning of the loop, in the header for the loop, we split the string on those spaces. And the reason we know it's split on spaces is that we don't have an argument for split. And when you don't have an argument for split, it splits on spaces. And what does it give you back? Well, it gives you back a list where the members of the list are the text strings, right? So now we have a list that has all those things in it. It has a 77 in text, a 97 in text, etc. And then what's happening is that we are going to, in the for loop, we are going to iterate over this list, starting with position 0. And we're going to do an eval on the string value from the list to give us a number, a code num. It's always going to be an int, so we could have said int rather than eval. And that might have been better documentation, right? Maybe even a little bit safer, but eval's fine. Okay, and then on the next line, what we're doing is we're accumulating the message character by character. So you'll see we did a character-based accumulator variable. We initialized it right before we started the loop. It's called message. So we initialize it to the empty string. That's a typical thing you do for a character-based accumulator. And then as we ran around, as we got each of the characters, we concatenated it onto the end, and then we printed out the answer. And that's how we got what we got. Now that's how this character accumulator we've used here. It's pretty similar to one that I did in a tutorial when we were talking about chapter 3, but it turns out that this approach is not sophisticated. Okay, and the reason it's not sophisticated is that this line where we do this constant appending of characters onto the message, it creates a whole bunch of string objects. It creates a succession of them. And that's pretty inefficient. So before the chapter's out, we'll see an alternative to this that's really pretty straightforward and is the more standard way to accumulate a string. But this is the beginner way right here, and we're proud of it. All right, so let's move on from here. Okay. We already talked about why that works, so we're not going to go much further. Okay. Now, there are a lot of the methods for string that we haven't tried yet. Okay, we tried split. That's a method for string. Okay, each of our strings is an object. Objects carrying around their data and their behavior, and their behavior is in these methods, and the methods are like functions associated with each object. And the way that we call the method is we use the variable name dot method name. And we just did that in the last examples. If we go back to that code, when we did in-string split, okay, I'm sorry, did I? Yeah. So when we said in-string split, the variable name was in-string, and the method name was split. Now, why we're trying to split it with the argument I instead of spaces is a little bit odd to me. I don't think that matches the actual code that we have. Let's look. No. So that's a typo. Sorry about that. So if we look here, if we see in-string split, we can say, oh yeah, that's how you do the split. So we've already used the split method of the string object type, and now we're going back and saying, hey, this is a good thing. There's all kinds of services that you can get by virtue of the fact that we're using the string object type for strings. Okay, and we can try capitalize. That's going to capitalize just the first character of this string. Okay, we can do title, which puts it into title case. So it's going to capitalize the first character of each word. Okay. We can use the center method to create a string of a particular width that has the text that's already in S centered in it with an equal amount of spaces on the left and on the right. Now, implicit in this is that we pick a width that's wider than the text that's already in the string that we're trying to center. If we don't give it any extra width, well then we can't put spaces around it, right? We can do counts of substrings. Okay, so we can have a substring that we're looking for. It can be a single character or it can be a sequence of them. And we can count how many substrings are in the string that we're calling that on. So let's say we wanted to know about the frequency of the letter E. We could pass as an argument the string E. Suppose we want to find a position of the first occurrence of a substring in our string. Well, we can use the find method for that. Again, we pass it the substring, and the trivial case is where the substring is just one character. This join that we have here is super cool. We concatenate a list of strings into one large string using S as a separator. So we'll see how we use that in a slide or so, and it can be very powerful, especially for our string accumulation, our more sophisticated version of string accumulation. Just like we did with center, there's an ljust for left justify. Again, the width has to be wider than the text that's already there, or you're not really left justifying it, are you? We can change the case of the letters. So lower shifts everything to lowercase. L strip strips off leading spaces. We can say that we want to replace occurrences of substrings in our string. So we pass it the old substring, the one that we're looking for, and the new substring, the one we want to replace it with, and we can have it do more than one occurrence. It's going to replace all of the occurrences. So for instance, if we wanted to replace the letter E with the letter O, we would, as the first argument here, we would have a one character string with E, and as the second we'd have a one character string that's O. When we did find earlier, we were finding from the left side, which is the traditional way that we process a text. Unless we're kind of speaking otherwise, we're going from left to right, okay? Well, what if we want to find the last occurrence of a particular substring? Well, instead of find, we say rfind, so it begins from the right-hand side of the string. That can be pretty helpful. Suppose we want to write justify a string. Well, we use rjust. And again, the width has to be larger than the string if we want to get some justification that we're able to perceive, because we now have some spaces on the left. We can use rstrip in order to strip away trailing white spaces, which are typically the character space, but it could be some other characters that qualify, on the right side. We can use split. We've already seen it. It splits into a list of substrings, and the argument is the substring on which to split it, typically a single character. Two popular things to split upon are space and comma, or perhaps a semicolon, if we have either comma separated values or semicolon separated values. And then of course we can shift all the values to upper by using upper. Now, I want to pause here and just emphasize that all of these methods that we call on a string don't change what is in the value of the string object that we're calling it upon. Now that it seems kind of weird, okay? And I've recommended a video at lynda.com where there's a discussion of mutable and immutable objects, and you probably ought to play that, but I'll address it here as well. Strings are immutable, they're not changeable, okay? Certain other objects are mutable, they're changeable. So one of the differences that we said earlier in the chapter is that one difference between strings and lists are that strings are immutable, unchangeable, and lists are mutable, they're changeable. Okay. Now, why do we make strings immutable? Well, it turns out that it's good for certain things in the kind of the logistical implementation of the language. One good thing about immutable things is you can pool them. Well, what does that mean? Well, that means that if in fact we have a lot of code in our module that we're compiling, and we use sort of a single character lowercase y over and over again, well then it's possible that we can use the same object multiple times, because if we create a lowercase y and we share it between different parts of our program, we don't have to worry that one part of our program is going to change it to an uppercase y and the other part of the program is still thinking it was a lowercase. That's not going to happen because it's immutable. So that's the key thing that's good about it. You can do this thing called pooling. It's also true that immutable objects are particularly good for certain algorithms that are big data oriented. Things, if you've got data that's going to be shared by multiple processes at the same time, where you're, say, running, well, let's just say you have a PC it's got 4 cores on it, like I do here. Actually, mine has, I think, 8 cores that look like 10, or 4 cores that look like 8, I think. Well, it's a lot easier to share these processors and do work in a multitasking environment if you know that the values that you're working on will not change. So even though it seems like a pain that strings are immutable, it's a very modern thing, and it kind of makes it a little bit hard to think of them for a bit, but once you got it, you got it. So, for instance, every time we call one of the methods that appears to change the value of a string, what really happens is that method is passing us back a return value of a new string. okay? And because of the way assignment statements work, it just leaves the variable that we're assigning it to not looking at a new value in the old object, but just looking at a new object that has the new value. Okay, and it's pretty simple once you get your head around it. Cryptography is the thing we talk about a little bit. It's not a major subject for us in our version of this course, but cryptography is the science of processing information, most typically text, and keeping it secret through careful encoding and decoding. So cryptography typically uses encoding and decoding. And so when and of course when we do it with a cryptographic approach, it's the encoding is encryption and the decoding is decryption. So encryption could be used when we're trying to transmit a credit card or other personal information to a website. The strings are represented as a sort of encoding problem where each character in the string is represented as a number. The code that is mapping between the character and the number is an industry standard, so it's not secret. Okay, now that's what has happened for us with the encoding we've done so far. We've encoded the characters to Unicode. Well, that's handy, but it's not at all secret. It's very, very public. If you want to get that encoding information, just go onto the web and look up Unicode and look up the code points, and you'll see the system that we're using. And of course, you can write the program to run it backwards. The encoding and decoding programs that we wrote in the chapter here, they use an encryption approach called substitution cipher, where each character in the original message known as plain text, text in the clear, is replaced by a corresponding symbol in the cipher alphabet. The resulting code is known as a ciphertext. This type of code is relatively easy to break. Each letter is always encoded with the same symbol, so using statistical analysis on the frequency of the letters and trial and error, the original message can be determined. Okay, so it turns out that the most frequently used letter in the English alphabet is the E. And then it goes, I think it's E-N-T-A, blah, 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 blah. You can look it up, all right? So what you do is, you go through the codes and you say, well, here's their frequency distribution. Okay, my first guess is they match the frequency distribution in English language documents, and the fact is you won't be too far off. So that's not really good enough for useful encryption for commercial enterprises, and certainly not for governments, right? So modern encryption is more sophisticated than that substitution cipher that we used in the programs that we already created. They convert messages into numbers, and I guess to some extent we've already done that. We did convert it to numbers. So we kind of did part of each. But the numbers that we convert them to are use more sophisticated formulas. So we convert the numbers that are we might convert it to Unicode, but then we run it through a mathematical function, through a formula, which gives us another number that we put there in its place. Usually the transformation consists of combining the message with another value called the key. So to decrypt the message, the receiving end needs an appropriate key so the encoding can be reversed. So that's a one-key system, often called a private key system, because you wouldn't publish your key, because if everybody knew it, well, then that wouldn't be very secret, would it? So single key systems are called private key systems. The keys are typically a number. It's not usually expressed in decimal. You often see them in hexadecimal, or even a combination of decimals in all the alphabet. So there are a lot of potential values for each of the places of the key. So private key systems work well for people who are well acquainted with each other. They're on the same side, right? They're both the CIA, right? Public key encryption has two keys, and it's pretty neat stuff. There are two numbers that are chosen that have a relationship to each other. And one is used to encrypt the message, and the other one is used to decrypt the message. And the encryption one, well, you give away, you make it public. That's the public key. And the decryption key, you keep that private, because you only want you and your close associates to be able to decrypt the message that is sent to you. So this all works pretty well. The interesting thing about modern public key, two-key public key encryption systems is the numbers that we use have a lot of digits. And the number of digits really determines how feasible it is to crack the code by simply brute force computer algorithms. And the ones that we use these days, I think we're up to about 256-bit keys, something like that. The keys that we use these days are still not crackable even by, certainly not by normal computing. Whether governments can do it or not is an interesting issue. But it's the same kind of thing that we did with text to numbers and then numbers to text, with a lot of very interesting transformation formulas in between. It's not so direct as simply calling the functions to get it into Unicode and back out of Unicode. So that's what's going on with that. Okay, now we're going to talk about input-output. Okay, and you'll recall that most of the patterns of the programs that we've seen in the book or we've created for exercises so far, they have followed this kind of general pattern of input, process, output. Okay, and you're probably not going to be too surprised that we can think of manipulating strings as input and output. Okay? So what we're going to do is we're going to talk about input and output, particularly in terms of string object capabilities. And then in the end of the chapter, what we're going to do is we're going to introduce files And we're going to talk about the capabilities of file objects. And we're going to find out that they're very similar. So thinking about input-output, even when you're dealing with strings alone, is a useful thing to do. Okay? So often we need to do some string operations to prepare our string data for output. We have to format it or pretty it up. Let's say we want to enter a date in the format 05/24/2003. Boy, that's a long time ago. And output May 24th, 2003. Well, how could we do that? Well, here's a kind of a pseudo code for it in bullet point order. Input the date in that month, day, year format, and put it into a variable called dateStir. I want to point out that our author doesn't really follow the hard and fast rules for forming variable names in Python. The hard and fast by the book one is that we don't use camel case capitalization. We separate the words with underscores, and we make the letters all lowercase. But there are people who will follow this protocol. This is the standard for forming names that's used in Java. And there's a certain camp in Python who have said, I think that's a better practice. We're just going to use that. I mean, it reads just as well, okay? I think that it's more important that you do it consistently than you do it one way or the other, okay? People who are reading your programs should be able to expect a certain kind of standardized naming convention for the names that you're using. I've been using the standard ones that go with the recommendations from official Python. I think those will serve you well, but if you decide that you want to do what the author is doing, well, I'm not going to penalize you for it. But you better be doing it one way and not both ways. So we get the data in, we put it into date string. Okay, I'm going to say that's probably a string, okay, just because of the name. And then we split a date string into month, day, and year strings. What can we split on? Well, I'm thinking the slashes are a good thing to split on. We want to convert the month string into a month number. We want to use the month number to look up the month name. Now, we did that before, and we didn't show the sophisticated version of the list that had the longer month names. We didn't show that working, but we will now. Create a new date string to form month, day, comma, year. So that would be like January 1, comma 2017. All right, output the new date string. So this is pseudocode for the way we're going to do this. And instead of going with his play-by-play, I'm going to go with my own, because I like mine better. Okay, so does he actually ever show us the code all together? He doesn't. That's bad. Sorry, I can't do it then. Can I? That's mean. All right. I apologize. So the first a couple lines are easy. We do an input. We don't eval it. We don't int it. We don't do anything because we want a string. So we put it in date string. A lot of times what I'll do is I'll call it something like date as string. Okay, so we know what the date is. And if it's important to remember that this one's a string object, I'll just say date as string. Date stir, that's probably just as good. So he gets a date string, And now what he's going to do is pretty interesting. In the next line, okay, he does two things. One is he does a date split on slash. Well, what does that create? That actually creates a list with 3 members in it. Again, they're still strings, right? And the first one should have the month, the second one should have the day, the third one should have the year. But does he assign it to a list? No, he doesn't. He says he wants to assign it to 3 variables. And so Python, being as smart as it is, splits this, creates a list, takes the list, and then populates these 3 things out of member 0, member 1, and member 2. Okay? So do we ever see the list? Well, not in this line of code. Is there a list kind of under the covers? There's definitely a list under the covers. Because if you look at the definition of split, what does it return? It returns a list. Okay? It's just that you can take a list and distribute the members like this when the number of variables that you're distributing it to is the same as the number of members in the list. Pretty cool, huh? So the data is input as a string and then unpacked into 3 variables by splitting at the slashes and using simultaneous assignment. He doesn't mention the fact that there's a hidden list in between, but I thought that you should know that. The next step is to convert the month string into a number. Okay, we're going to decide to use the int function to do that instead of the eval for 2 reasons. Reason 1 is that int is really better documentation. These are integer values that we're trying to create. Okay. Number 2, it turns out that eval doesn't like leading zeros. And if you read in the text, there's some horrible, sad, historical reason for why that's true. Okay? One of the reasons why I never liked Python for a long time, and only recently have become the convert that I am, because they put a lot of those kinds of problems to rest. Right? So we want to use int because it's good documentation, it will work. That's going to give us a 5 for the month. Eval won't work because of the leading 0 in the historical baggage. Okay, having to do with octal, which is a based 8. And octal is so old. Okay, now we're going to create a months list, okay, it's all populated with the full month names, 12 members in that list. And then we're going to say month string equals months. We're going to pick it out. And how are we going to figure which one? Well, we're going to take int of month string. That's going to get us an integer version of the month. And then we're going to subtract 1 because you remember they're numbered 0 through 11, not 1 through 12. That's going to pull out the right one. Okay? So now let's concentrate on the output string. So now we want to print the converted date is, okay, we don't have to put a space in here because we get one automatically because we have the comma separator here. And then we have the month string, okay, that's populated with the full word, comma, day string. Notice we never have to convert the day string. Okay, we didn't have to do any math with it, right? But we want to add a comma after it. So we say day string plus just a comma. So now we're going to get value comma. Then we'll get a space just because of the way these commas outside of the parens work. I mean, outside of the quotes work. And then year string. Note that we never converted year string to a number because we didn't have to. Pretty cool. So we run our program and we say enter a date. We put in 01/23/2010, and then we get back January 23, comma, space 2010. Okay? So this was your basic input, process, output stuff. Are we using strings? Sure, we're using strings. Okay? In fact, all of our work was done with manipulating strings except when we converted the month to an int in order to create the appropriate index to retrieve the month name. Apart from that, it was strings in and strings out. Are we using files? Well, we are implicitly, okay? In the code where we do an input, okay, we're using a standard input file that's associated with the console. So when we type on the console, that's creating an input file. We haven't worried about that a lot yet, but we will later in the chapter. And then what about the output side? When we print things, we're really printing to a standard output file. So there's a standard input file associated with the console and a standard output file associated with the console. And when we do one of those calls to input, to the input method, well, we are implicitly using the input file. When we make a call to print, we are implicitly using the output file. Sometimes we want to go the other way between strings and numbers. Okay? We've talked about how to turn a string of digits into a number. We would do that with either eval, or if it was an int, probably better to use an int. Or if it's floating point, probably better to use float. Okay? Eval will handle them both, but sometimes we don't want to handle both. Sometimes we want to make sure that we're getting what we expect. So if we say string of 500, we can just get the character string for 500. If we say string of something that's 3.14, we'll get 3.14. And then we can say the value is string value plus period. Now, I just want to point here's one of the reasons that you want to do this, okay? If, in fact, you just put value there, okay, it would think that you were trying to add value, which is a number, to a period, which is a character string. And it doesn't like that because they're two separate types. It doesn't know if it should add them or concatenate them, okay? The value, your motivation for using a call to this str function here is that once you turn value into a string, then it's obvious to Python that you want this plus to mean concatenation. Okay? We typically can get the print to print out a string equivalent to the value inside the variable simply by using the variable name. But then we're not able to concatenate the period onto the end of it. So this is one of these kind of special use cases that you need to get the pretty formatting that you want. Okay. So slide number 66 shows you what goes wrong if you did not convert, if you didn't call if you didn't call the stir method with value. It thinks that this is addition, and it doesn't like it. Okay. So we now have a complete set of conversion operations for between strings and number types. Okay. So we use float to convert a string into a float. We use int to convert a string into an int. We use stir or string to convert a number type, either int or float, into a string. And we use eval to create convert a string type, either an integer expression or a float expression, into either an integer, either an int or a float, depending upon what's found in the string. So it's either going to get an int, a float, or an error. Okay. If it says, if you do an eval on the value 1, you're going to get an int with the value 1. If you do an eval on the value 1.0, you're going to get a float with a value 1.0. If you do an eval on a string hi mom, you're going to get it's going to throw an error. Okay. Here we come up with a program that's a pretty popular program. This, I've probably taught this or done it in almost every programming course. This is a program that helps us to count up change, right? The change counter program. We may have seen an early version of this. I forget. I get my books confused. I apologize for that. But what's going to happen is that this change counter, we're going to run it, and it's going to ask us, it's going to prompt us for how many quarters, how many dimes, how many nickels, how many pennies. Apparently we're not interested in half dollars or dollars. Okay, we're not interested in those coins that circulate but not as frequently, right? But we could extend the problem to include them if we wanted to. That'd be a good exercise. And we have 6 quarters, we've got 0 everything else, and it says the total value of your change is 1.5. Okay, shouldn't be more like $1.50, not question mark, question mark. That's part of the bullet, not the value. The value that we're suggesting is that one. Yeah, well, that would be better. That's more user-friendly. So how could we do that? So it's possible to use formatting templates when we are printing. And this really gives us a lot of control over the formatting of numbers and how they appear. And this is the preferred approach, okay? So, one of the things that we could say is we could say print the total value of your change is, we have a $sign, and then in curly braces, we have something that's going to be replaced by the value of a variable. So we've got 0:0.2f. I wonder what that does. Well, here's what we got. We got $1.50. Well, that gave us what we wanted. Let's go explore why that worked. Okay. Oh, and I want to mention here, look what we have here. This first part is really just a literal string. Okay. And we're calling a method on it with the dot notation. So we're calling its format. Okay. So strings, okay, have a format And then what are we passing it in? Well, we're passing in the variable, which is going to pass in the object for total. In this case, I think it's a float. Okay? So notice this template phrase is inside of quotes. And then there's a dot format. And then we're passing values in as arguments to the format method. Okay, so this is a template string. There's a template string on the left. It's in quotes. It's in quotes because it's a string. Because it's a string, it's an object, and we can call dot format on it. Dot format is expecting us to send it a series of values, typically numbers, that it's going to plug into these slots in the string. Well, how do we know how many slots there are and where they are? Well, there's a slot every place that we have a curly brace pair. That's how we know that. That's how we know where to place the values from the variables. So we typically are going to have a one-to-one matchup between the variables that we're populating the template with and the number of these curly brace slots. So let's back up one. Okay, how many curly brace slots have we got here? Well, we've got one. And how many variables are we passing as arguments? Well, good thing we've got one as well. And then how are we going to format that? Well, we're going to look inside the curly braces for the format specification. Pretty cool, huh? Okay, let's get some more details. Each slot has a description that includes a format specifier or specification telling Python how the value of the slot should appear. Now, I've got to warn you, when you first come to this, you go, oh, this is maybe not intuitive. This isn't the way I think. Okay, and I to tell you the truth, these format specifiers are something that I found kind of unappealing for 40 years. I mean, I go back to the days when I was learning Fortran and we had these things, and I didn't take to them very well in the beginning. So I've always been a little reluctant around format specifiers. So if you feel a little reluctant to learn how to code it, well, just get over it a bit, because it does come to you and it creates a lot of value. Okay, this is much easier than doing it by other means. Okay? So here's an example here where we say, it's the same example that we had before. So what's inside the curlies? What's the specifier? Well, 0:0.2f. Okay. So the text has two parts. On the left, we have an index. Okay, and on the right, we have a format specifier. Okay, on the left, we have an index. Here, it's 0. And on the right, we have a format specifier. Here, it's 0.2f. Okay, there you go, right there. All right, that makes sense. So let's see what goes on with the index. Okay, the index tells which parameter to insert into the slot. In this case, total. Okay. Total is the first parameter. Okay. Then why do we put a 0 here? Oh my God, we're starting at 0 again. Okay, now if you come from my school, it's like start tearing your hair out. Right, but I'm used to it. I've been doing these things that start with 0 for a good 20 years. Okay, I don't like them, but I've been doing them. Right, it isn't like they were just introduced to me yesterday. So 20 years is a long time, but still, I wish they hadn't. Okay, so if we want to say fill this with the first parameter, the index is 0. If we wanted to fill it with the third parameter, the index would be 2. Isn't that appealing? Well, I'll bet you get that wrong a time or two before you remember, oh yeah, we're counting from 0. Okay, so what about the format specifier? Well, we've got 3 parts to it. Width, which is a number, dot precision, which is a number, and after the precision number is a type, which is a character. Okay, so let's see. Width dot precision type. Let's look back and see what we have. So width 0, precision 2 decimal places in this case, type fixed. Okay, so we want to format it as a fixed number. And you might want to say, well, no, we only have 2 number types so far, Kevin. We have a float and an int, and neither of those is called fixed. And I'm going to say that this is more of a formatting type. Okay, we want to format it in a fixed number of digits, 2 decimal digits. All right. Okay, so F means fixed point number. That's what we want to write out. Okay. Width tells us how many spaces to use to display the value. 0 means to use as much space as necessary. And I'm not going to complain about that 0 because, number 1, we're not counting. Okay. And number 2, if we're going to use an integer value to specify it, 1, 2, 3, 4 up to 1,000,000 or whatever, well, they all have a meaning. So we're only left with 0 and the negatives to say, do what you want. So does it bother me that we use the 0 to say, do what you want? No, that's a pretty common trick. And so I'm happy with that. So in this case, we use 0 that says, just take the space you need. If in fact we give a larger number, well then one of 2 things can happen. One, if the number is not large enough, then we're probably going to be chopping off a part of the digits that we're interested in. If it's larger than we need, then we're going to have white space. We're going to have extra spaces. Okay? What's precision? Sorry about that, guys. Now I'm lost. Don't you hate that? Oh, there we are. We're on 72. What's precision? Well, it's the number of decimal places. Our precision was 2. We had 0.2 F. So our width was 0. Our precision was 2 decimal places, and F says fixed point. So when we say fixed point, the precision of 2 means that it's going to be 2 decimal places to the right of the decimal point, which is what we got. Okay? So here are some uses of the formatting function where you can get some idea about what's possible. So this first one has 3 slots numbered 0, 1, and 2. Okay. I take that back. They're not numbered 0, 1, and 2. I mean, they are 0, 1, and 2. But in this case, we're going to get Mr. Smith. Hello, Mr. Smith. You have won $1,000. I don't have a good explanation of what 0 and 1 are here. Oh. Again, it's the index. It's what I said to begin with. It's a little early in the day. Sorry about that. So if we don't have anything else, we have the index. This is slot 0, slot 1, slot 2. How do we fill them in? 0, 1, 2. Okay? We didn't ask for particular formatting. Okay? We just had it control where it goes. Okay? So now we come down to the second one. We've got one slot 0. We're saying that it has a width of 5. Okay? We're not trying to control the decimal places, so it's just 5. Okay? And what are we putting in? Well, the 0th value is 7, but 7 only takes one space, so as a default, we fill it in with 4 leading spaces on the left side. How do we know if it's going to be on the left or the right? Well, the default for numbers is that they're justified to the right. The default for text, strings, if they're justified to the left. We can override that, but that's the default. Okay? Here we're doing a very similar thing in the next line, but we're saying the width is 10. And then, of course, we give it the value 10. And for what you can see here, we just have more leading spaces. We should have 8 leading spaces. Well, probably 9, because there's one here. Okay, so we should probably have that one plus another 8. So we should probably have in here, if we counted the spaces, we should see 9 of them. Okay, so now this float, again, index is 0, 10.5. Okay, so 10 wide, a precision of 5. Now, you notice that there's no F. What does a precision mean if we don't say F? Very interesting. Let's go down here. Okay, so we've got some approximation of a number here, 3.14, blah, 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 blah. Okay, and how many digits of precision do we really have when we start? 1, 2, 3, 4, 5, 6, 7, 8. That's going to be in a float. Can a float hold 8 digits of precision? Sure it can. That's going to be fine. So we have the detail in there if we want to use it. What do we tell it? We say use 5 digits of precision. So what do we get? Well, we get 3, 1, 4, 1, 6. So 1, 2, 3, 4, 5. So it starts in the beginning. 1, 2, 3, 4, 5. Instead of getting 5, it rounds off the last of the digits. Okay? So that's how we got 4 decimal digits, and the last one of them rounded. What if we wanted to, of course, if we had a higher number, if we had something that had 2 digits to the left of the decimal point, and we asked for a precision of 5, well then we would only get 3 digits to the right of the decimal because we'd be using 2 to the left. So that doesn't always give you the control that you want. Typically, the control that you want in some kind of a business context is that you want to control what's on the right side of the decimal point. Here, in this last example, we've said we want this to be fixed point formatting, and we want it to be 5. So what does that mean? Well, when you say 5F, that means 5 to the right of the decimal point. Now, how many do we have to the right of the decimal point? 1, 2, 3, 4, 5, 6, 7. So 6 and 7 are going to be ignored, or they're going to be rounded in. Does 2, 6 round 9 up? No, because it's less than 5. Okay, so we're just going to stop with a 9. So I'm going to expect 3.14159. Hey, that's what we got. Do we have any extra spaces here? Yeah, we have extra spaces on the left because we asked for 10 spaces. So again, there's a lot of moving parts, but the little experimentation, I promise you, you're going to get it. Because if I can get it, you can get it. I don't take naturally to these myself. They're very mechanical for me. I never loved them. But they're, for me, they're a very happy, necessary evil. And if you want to be good at formatting things, you had better learn it. Okay, if the width is wider than needed, numeric values are right justified, strings are left justified by default. We can override that if we want. Okay, so here we have left justification. That's all text. One of the things you have to remember that these templates are a combination of the text that we want to print plus these placeholders, right? So the beginning of this, I mean, some of the text that's in the string is what we're really going to print out, and some of it is going to be replaced, namely the things that are in the curly braces. So we get left justification colon, and then we get what we get in index 0, which is high. We say that we want it to be 5 wide left justified. Okay, so that comes out left justified plus we've got probably 2 more spaces. Did just what we wanted. Here we say we want it to be 5. Oh, that's left justified because it has a less than sign. It points to the way that we want to justify it. Pretty easy to remember. I mean, it's kind of intuitive. On the next command, we're giving it the right justification symbol. Okay. And that's going to cause it, again, to be still in a 5 wide field, but contrary to the default, it's right justified. The default would be left because it's a string, but because we put that greater than sign there, now it's on the right side with the padding on the left. What if we wanted to center it? Well, we use the caret, okay? And the caret, I guess, makes sense. If you justify to the left with a inequality signing that points to the left, and if you justify to the right with an inequality symbol that points to the right, then a pointy arrowhead thing that points to the top, you can imagine how that might say, well, I'm pointing to the middle. Okay, here when we do that, the extra 2 spaces, we get 1 before and 1 after. And 1 before. I can't find my 1 before, but that's it. Pretty cool, huh? Okay. So better change counter. Oh, this is actually going to turn into the program I thought we were going to see earlier. So what we're going to do is we're going to write a change counting program that takes advantage of some of our recent skills, okay? With what we know about floating point numbers, those are floats, we might be uneasy about using them in a money situation, okay? And I'm going to say you don't want to count money in floats, not unless it's real big of values that you're using for some kind of a forecasting operation, okay? And you're forecasting things in thousands of dollars. Well, floats might work just fine there. But if in fact you have an accounting oriented application where you need the balance to the dollars and cents, floats have too much distortion in them, so you don't want to use them. Now, there are several ways to fix this. One way to fix this is to just use an int and have it be pennies, okay? So we know we can keep track of pennies if we express it as pennies, that we know we're accurate to the penny, right? Which is what that accounting typically is. And then when we go to output, we'll just convert it to dollars and cents when we output it. Typically, we can do that by dividing by 100 and giving it the right formatting. So that's the solution that we're going to use. Is that the solution that everybody uses in place? No, we're eventually going to find out that there is a common module that we can import and use that has classes that have objects that we can use for currency that are more appropriate than certainly a lot more appropriate than floats, but more kind of better documentation than this doing your math with pennies and then converting on output. But for right now, that's our method. Do our math in pennies and convert on output. Okay, this also gives us another great use case for integer math. Okay, you'll remember that in Python 3 that if you use the slash to say division, you're going to get floating point division. So you're going to get back a floating point number that potentially has a fractional part. Okay, if you use the double slash like we have here, okay, then you're going to get the whole part. So if we integer divide the amount in cents of our cents by 100, the result is going to be whole dollars. It's going to ignore the cents. And then if we use this modulus operator, this remainder operator for cents, well, then we're going to get the real cents. Now, I've got to say that the way that the author is handling the variables here is kind of a cavalier, okay? Because up here he's saying that cents is an int, right? And then he's taking the dollars and then he's recalculating the cents to be the part is not the dollars. And I guess that's true. I mean, we've taken the dollars away from it, so the cents are going to be less. I would tend to call this initial value in cents something and not be destroying its value. And then I would tend to call the dollars and the cents would be the computed values. And I wouldn't be wiping out my original total count of pennies because I just don't think it's a careful programmer thing to do. Then cents is printed using a width of 0 right inequality sign 2 to right justify it with leading zeros if necessary. Remember, we could have less than 10 cents. So if we have 9, we want it to come out 0.9. If we have 5, then 5 cents becomes 0.5. All right, let's look at this. It's a little easier to see it here than it is in the pie charms, so we'll look at it here. A program to calculate the value of some change in dollars. Okay. So in our main is where our code is. Do we actually show? Yeah, we do show a call to main. No, we don't actually show the call to main. Oh, I see. He types the call to main in at the console. That's not the way we do our work, but that's okay. So in the main, he prints a polite message then he prints, please enter a count of each coin type. Okay, and then he's going to further prompt. He does the quarters. So he does input for quarters, he evals it. He does input for dimes, he evals it. Input for nickels, he evals it. I want to point out that for my money, is it possible for us to get fractional quarters? No, it's not really possible for us to get fractional any of these quarters, dimes, nickels, or pennies. So instead of calling eval, I would have been happier if he called int. Okay? Because at this point, if they gave us a bad value, like 10.5 quarters, we'd blow up. At least we know that we gave a bad value. We don't have the sophistication to fix that yet, but I'd like to guard against it. And then in the end, he says the total is quarters times 25 plus dime times 10 plus nickels times 5 plus pennies. If he was on my team, I'd break his legs. Okay? I'm sure he doesn't care. But for me, I don't want the people come behind me to have to remember that the multiplications are going to be done first and then left to right. So first we're going to do quarters times 25, then we're going to do dimes times 10, then we're going to do nickels times 5, then we're going to add the first product to the second product to the third product to pennies. Put the parentheses in, guys. It doesn't take, it's not, there's no cost to being clear about what your intentions are. You know, the fact that you know the principles of these expressions both in math and in computer languages, this order of precedence stuff, that's great. Okay, I don't want you rubbing anybody's nose in it. Put the parens in. I hate it when a guy does stuff like this. And then he prints, let's see, what does he print? The total value of your change is, he's got two slots, okay? The first slot is 0. The second slot is 1. What's in between the slots is a decimal point, okay? So, in the first slot, does he say anything about the width or anything like that? Nope. He doesn't. He's just going to take the default. It's going to justify right. It's going to use just the width it needs. Okay, that's fine. For the pennies, he's doing the same thing. He isn't saying anything about the width. Okay. And he's saying that he wants a precision of 2. Okay. Now, you know, then he says dot format. The string is just the template dot format, and then instead of having pre-calculated the values up here, which he could have done, he decided to do the math right here, where he passes them in, passes the dollars and the pennies in as arguments to format. And I think I've been pretty clear. I believe you can do it either way. There is a time when the calculations are so complex that putting them in the print statement is bad practice, because it's very hard to read the print statement. But right here, it's a matter of what your preference is. Then he calls main, prints out change counter. He gives all zeros and then 1 for pennies. So the total value of your change is 0.01. Well, that looks good. Okay, and that's pretty good testing, because it's pretty close to what I call a boundary value. Okay, that makes sense. What about 0. Well, I might try 0. I probably should come out to 0. And it probably should look just like that thing does on the left, except that it doesn't have a 1, it has a 0. Okay, that's good. And then on the right, he gives more reasonable values, 12, 1, 0, and 4, and he's saying value change is $3.14. That looks like it's properly formatted too. Would I want to do any more testing? Yeah, I'd probably want to know what happens when I give it 1,200 quarters. I want to know if this thing really formats out, and so instead of $3, that's what, $300.14. I want to see if it looks like I lie. What if I want to see if a comma comes up? And I don't think a comma does come up. Okay. But what if we give it 12,000 quarters? Okay. Just want to see what it looks like, if it's really behaving like I'd like it to behave. With what we have so far, we're not going to get a comma, but we would get $3,000.14. Okay? And on the other side, I'd want it to work with 0. Negative values are not sensible. They're probably going to get us problems with our math. They're probably going to get us some bad results. Later, we're going to learn how to protect against unreasonable values on the input side. But we're just going to assume right now that they're going to follow, that we have a reasonable user. That's always a dangerous assumption, but that's all we can do now. Okay. So I just want to show you that one working. Okay, so where's change 2? Here's change 2. All right, and that's working fine. And let's do a little of that testing that I said. So let's run it. So let's give the two cases that they had. We had 0, 0, 0, 1. Oh, sorry, that's not it. 1. Ah, that looks good. Okay, let's run it again. Okay, and I forget what the values were. Let's cheat and look. They were 12,104. Okay, so let me bring this back. 12,104. Okay, $3.14. That looks good. Okay, and let's just instead of 12 quarters, oh, we didn't do 0. Let's do 0, 0, 0, and 0. 0.00 looks good. Let's run it again. What happens if we say -1, 0, 0, 0? That's not what we're expecting. Okay. Number one, you can't have a -1 quarter, and number two, I mean, you either have quarters or you don't. I guess you could think of that as loans, but even if that means that we owe a quarter to somebody, that doesn't mean that we have a negative $1.75 in change. So that's given us a wrong answer, which is why eventually we're going to need to protect against that kind of input. If we don't protect against that kind of input, if we want to support negative values, is saying that, well, these are values that we owe to somebody who we borrowed some change from at lunch, then we had better get the math to work correctly, because right now it's giving us a wrong answer. Okay? All right, and let's go with the big values. Okay, let's say if we have 1,200 quarters, 0, 0, 0, $300. Okay. Let's do 12. Sorry. let's do 12,000 quarters. 0, 0, 0. $3,000. Notice that there's no comma, but it seems to get bigger just fine. So that, I think, is kind of adequate testing strategy there. We want to test the boundaries of that value. What happens if it's very small? What happens if it's very large? What happens if it's 0? What happens if it's negative? What happens if it's incredibly large? Okay, let's try one more. Let's give it 99,999 quarters. 0, 0, 0. Well, it's almost $25,000. That looks good. Okay, and that makes sense, because if it were one higher, we'd have a whole dollar, and it looks like we'd have $25,000. So it's that kind of thinking where we want to bracket the values. This is often called boundary value testing. That's what we want to be doing. And aside from the fact that we didn't get what we wanted with a negative value, everything turned out great. Okay. Now, let's finish up the chapter by talking about strings. Okay. So most of us are acquainted with files, right? We use text files pretty frequently, and we do it with a word processor or a text editor. We know that our proprietary applications like spreadsheet programs, word processing programs, we know that there's a bunch of characters inside their files, but we can't always make sense of them. They're in a proprietary format. But if we use a text editor, we can open up our file with the text editor, and it kind of makes sense. It's just as we put it in. Okay? So the kind of files that we're talking about here are those text-oriented files, where you can think of them as in two ways. You can think of them as a big line of individual characters, okay, or you can think of them as lines of text that end with a new line character. So you can think of it as one big string of a file, or you can think of it as one line of the file at a time, or you can think of it as one character at a time. Files can contain any data type, but the easiest to work with are text. A file usually contains more than one line of text. Python uses the standard new line character, which we code in a character string as \n. Of course, when we do that, it's typically inside of quotations or apostrophes to mark the line breaks. Okay, so hello and world are strings here. So what do we have? We're trying to write out 1, 2, 3, 4 lines of text. One that says hello, then world, then blank, then goodbye, space 32. How could we do that? Well, if this were a print, if we wanted to be able to print this, we would say print, and here's what we would pass it. There'd be a character string, okay, with quotes, and then every place we wanted a new line, every place we wanted to break the line, we'd have a \n. Okay. Now, is there really a \n there? No. \n is what we call an escape sequence. That means that when the compiler is looking at the string that we give it, when it's looking at it, it goes, oh, \n, I'm going to put the value in there for a new line. Okay, so what exactly are we saying here? Well, this is the encoding that we give literals in our program. This is what it looks like in our program. Okay, so let's take this. Let's go look at PyCharm. Okay, let's close the close the console we have. Let's open another console. Okay. And let's just put in a print. Okay. And then let's put in a character string. And there's the characters that we saw there, including the \n, would go right into the character string. I just did a paste. Okay. I think you can see that the \n are telling us that they're coded in a little different color that says they're escape character sequences that are going to be replaced by new lines. Okay, so in our code, they look like \n. Okay, let's run this. In the output, they look like this. Okay, every place we had a \n, we got a new line. So when you actually write a new line to a standard output file that's coming out on the console, you don't get a character, you get a new line. Okay? It's an action-oriented code. It's not a glyph. It doesn't have a glyph associated with it. It has an action associated with it. Okay, well, how would this look in a file? Well, in a file, how do we know what's in a file? Well, we can look at it in a text editor. Well, let's just take this, copy it as plain text. Okay, let's just take that. Okay, and then let's create. We can actually create. We can go up to the menu and say File. Oh, sorry, no, we don't go up to the menu, but here we can say New, and the first entry says File, and we're going to give it the file name, and we're going to call it my new line example. It's text, so it's going to get it in a .text file. Say OK. And it opens up in the editor and it's blank. So what happens if I paste that stuff in? Well, look what's there. You get the same kind of rendition when you open a text file in a text editor. Is there a character associated with the new lines? Well, it's an action-oriented value. So we've got 1, 2, 3, 4 new lines here. And what do we get? Well, we get 4 new lines. That's what we got. It's very action-oriented. Okay? So what's interesting is that when you open up a text file in a text editor, it looks pretty much the way things would have come out in the console. So what we're actually going to do is we're going to learn to write things to an output file. Okay, and guess what? The writing is going to be with print, and it's going to look pretty darn close to the way that we did it out to the console. Except that instead of going out to this standard file that shows up on the console, we're going to put it in a particular file. And so when we're done, let me save this. I guess it's automatically saved just like everything else. When we're done here, we've got this my new line example text, okay, and I find this, and if I open it with a double click, there it is. Okay, that's what it looks like. So to go back to the slide, to say that it looks like this when it's stored in a file is misleading. Okay, there are byte values that represent a new line action, okay, in those places. And is there any kind of editor that you would open it up where it would look like a \n? Not the editors that I use. The editors that I use, it would look like a new line, just like I just showed you, okay? All right. This is the same thing as embedding the \n in print statements. Well, we just saw that. Remember, these special characters only affect things when printed. They don't do anything during evaluation. Okay. Now let's talk about opening files, okay? Because this is kind of interesting thinking, okay? We're all used to having files in our operating system. And let's say we're only talking about text files, okay? Because that's all we're learning how to deal with now. So, so we have a directory tree, and at various parts of the directory tree, we have files, and they have a file name, a dot, and a file extension, like fred.txt, right? And what we want to be able to do is we want to be able to read from the file. One of the ways that we can manipulate the file is to read from the file. And the other thing that we can do is to write to the file. So those are the two things that we're going to learn how to do. Okay? Reading from a file is non-destructive. Okay? And we're typically used to this. We read the contents of a file. We don't expect it to be affected. Okay? Or affected. All right? If we write to a file in most technologies, we overwrite whatever is in it. And in fact, in Python, what we actually do is that we erase that old file and we create a new one. So that is destructive. So reading, non-destructive. Writing, you can think of it as replacing what's already there. And of course, if we go to, we can have some errors or some unintended consequences. For instance, if we tried to read a file and the file name that we're asking for isn't there, well, we're going to blow up. So if we ask for fred.txt instead of kevin.txt, which is actually there, when we go to use that file, it's going to blow up and say, well, I can't find fred.txt, okay? Or if we accidentally write to kevin.txt instead of fred.txt, we're going to write over top of kevin.txt, okay? Gone, splat, all right? So a little care is in order. We're kind of used to that because a lot of the products that we use have this kind of idea about files. Okay? In fact, I think there's a good discussion of it in the chapter. I forget whether we talk about it here or not. Let's go look. Yeah, we do that, but let's not go there yet. Okay, with the first of the bullets here back on 82 we've not talked about yet, and it's an important one. The process of opening a file involves associating a file on the disk with a file object in memory. Okay. All right. So this is something that is pretty interesting, okay? As we learn about these object-oriented things, okay, I've got you reading it, I've got you listening to lynda.com sections where we're talking about objects and we're kind of comparing them to clothing, right? And we talk about a red shirt and a crimson shirt and all this kind of cool stuff. I think you're going to like it. But it's pretty easy to distinguish between some actual physical object in the world and some programming system object, okay, that we create using an object-oriented language like Python that becomes a proxy for the real object in the real world. So we can have a red shirt in the real world, and then we can have a shirt type object in our application program that we say has the property red. So it's pretty easy in our mind to distinguish between the real object in the real world and the programming object in our computing environment. And we realize that there's an association between those two, and we don't get them confused all that often. Because we know that shirts are shirts and you're able to wear them. And we know that shirt objects are, and shirt classes and all those things are programmerish things, and that they're in our computer and you can't wear them. But you can do all kinds of cool computerish things with them. Now, there is a distinction of the same type between files that are real that are in your real operating system, Kevin.txt, Fred.txt, and the file object that we create in our programming environment to communicate with that real file. They're two different things. Okay? In this case, we are creating a file object to represent the file on the disk and to communicate with it and to manipulate it. Okay? Well, how does that help us? Well, it helps us because we're able to mix and match. Okay? One of the things that we do is that we can declare an input file in our program, and we might call it input file. Okay? And then we can associate that in different runs of the program with different physical files that are out on the hard drive. Okay? So, yeah, in both cases, we create an instance of a file object, but in one case, it's connected to Kevin.txt. In the other case, to Fred.txt. So, that's pretty powerful because it turns out that then we don't have to write a new program for every two particular files we want to work with. Input and output. We can write a program that generally has a text input file and generally has a text output file, and that we just have to associate the internal file object with that external physical file in the operating system. Okay, so that means in one run, I can read in Kevin.txt, and I can write out KevinReport.txt, and then in the next run, I can read in Fred.txt, and I can write out FredReport.txt. So we can mix and match and get some great power. How do we associate the actual files on the disk with these file objects? We do it with a method called open. So when we open a file, what are we doing? Well, we're calling opening on a file object. It's a file object that we're opening. And we're telling it to go out and communicate with the operating system and find the file by this name, Kevin.txt. And that'll work fine if there is a Kevin.txt. It's already there. Okay? If it can't find it, we're going to blow up. If I ask for Kevin.txt or Kevin.txt because I have a typo, it's going to say, I can't find Kevin.txt. Oh, sorry, I meant Kevin.txt. Let's run the program again. Okay, so it's this fact that we have these internal objects, these file objects, that represent the physical files on the disk, that allows us to do this mixing and matching that makes these programs much more valuable to us. We're used to doing things like this in programs that are written by other people, but we haven't really been able to do that for ourselves yet. So what we're going to do is we're going to open a file for reading, we're going to open a file for writing. Typically when we do these things, The kind of things that we're going to be doing in this chapter are input, process, output. Okay, so we're going to have two files. We're going to have an input file and an output file. So when we open them, we're going to associate them with physical files on the disk, hopefully the right ones. And then to get the input from the input file, we're going to issue reads. And to send the output to the output file, we're going to issue writes. And then when we're done, how do we make sure we're done? And all the things that we wrote are actually flushed out and in the physical file. Well, there's another operation, the kind of corollary or obverse or whatever you want to call it. It's a close. So what we typically do is we open the input file, we open the output file, then we do the processing for a while, typically in a loop. That we get done and we're doing reading and writing and reading and writing and reading and writing in the loop over and over again until we run out of input. Then we write the last of our output. Then we get out of the loop, and the last thing we do is close the files, usually in the same order. We usually close the input file and close the output file. So that's what our program is going to look like in a couple of more slides. Okay? So this opening and closing is what allows us to associate and disassociate those file objects with real files out in our disk drive. They both seem like computerish things. Both the file that's on our disk drive and the file object that's associated with our program. And sometimes you can go, well, that's not the same distinction as a shirt object in our program and a real shirt in the world. But for our purposes, it's a very like distinction. Okay. All right. Now we're used to processing files in programs like word processors and spreadsheets. And they work a little different than the way we're going to work inside of our program. Typically, when we say that we want to open a file, it opens the file, it reads the contents into memory, into RAM, it closes the file while we're working on it. And the changes that are being made while we're working in Word or Excel or whatever are typically made on in the memory of the computer in the RAM until we're done. And it's only when we save it that our changes actually get saved out to the file. So it's pretty, one kind of similar thing here is that yes, there is a file that gets opened, and yes, there are a lot of reads, but pretty typically what we do is we open the file in these applications, we read everything into memory, we work in word processing or spreadsheets. All the changes that we make are made to memory, and then we say we want to save it. So we open the file again, and then we rewrite the entire file, and then we close it. Okay. Now that's not the kind of model that we're going to be using. Okay. We're not going to be doing all of our work in the memory. We're going to have a batch program approach, which is really one of the oldest approaches in information technology or data processing, whatever you want to call it. And what I learned years ago when I first got in, because that was the majority of things that we were doing. And we still do a lot of things that way. This is why we want to teach you. Okay? I already talked about the saving and all that kind of stuff. Okay. So, again, by comparison, what we're going to do in our file processing, our batch file processing, is we're going to open up an input and an output file, and we're going to read the lines of input one line at a time. We're going to process it, create one line for output, write it out to the output file. So it's going to be input, process a little, output. Input again, process a little, output. We keep going through that loop until when we go to get input, we go, oh, we're out of input. We go, okay, we're done. because we've already created all the outputs for all the inputs that we did have. Let's close the files and stop. So this is the classic batch processing loop that we're going to learn about. Okay, let's learn about the statements that make it go. The first thing is we need to associate a disk file with the file object with an open call. Okay, so we have a file variable. Okay, so we say the variable, it's a variable that is going to it's going to point to the file object, and we say open, okay, and we pass it a name and a mode. So what's the name? It's just a character string, okay, and the character string is going to be something like Kevin.text, okay, and it works pretty much the same way in Python as it works with the products we're used to using. If we just give a file name and an extension, then it looks for it in the current directory. What's the current directory? Well, for us, it's going to be our project directory, the same one that the program's in. Okay? So that's how we give it the name. The mode is going to be R or W. It's a single letter character string, lowercase, read or write. Okay? So an example at the bottom is we have infile, which is a bad name for a variable because it begins with a cap, so I'd rather have it be lowercase infile, equals open numbers.dat. Okay, that's a file in our current working directory called numbers.dat, and the function or the mode is R. We're going to read it. We're opening it for input. Then, once we have assigned, once we've done the open and we have that variable associated with a file object, then every time we want to do something with it, we use the variable name dot method. So if we opened it for reading, well, then we're going to do reads on it. Okay? Now, turns out that on the input side, there are 3 ways we can read input. Okay? The first one is we use the variable that points to the file object. In this case, it was infile, right? We say infile.read. We get back all the text that's in the file in a single string. So we would want to assign that to a name that we were expecting to hold a string. Okay? It could be big. It could be a very big string. Okay? Or, so we can read everything in one fell swoop, or we can say read line, which is going to read until the next new line. Okay? This is going to take all the text up to and including the new line. Oh, by the way, in the first option where we did a read, it's all the text including the new lines. Okay? We're not thinking them as new lines. We're thinking them as a special character sequence, but they're all in there. They're all in that string when we read it in and we put it into a variable. When we do read line, we just get the next line, okay? And again, we assign it to a string. And if you look at the last of the characters in the string, it's a new line. Okay? Or a very interesting thing that we could do is we can do read lines. That returns a list of the remaining lines in the file. Each list item is a single line, including the new line characters. Well, if we knew that we had a reasonably sized text file, we might be able to just do a read lines, put it all into a list, And then we would be able to process it kind of like we do in the word processor or the spreadsheet, where we have all the data in the memory at the same time. We just have to be able to navigate our way around the list. Well, that's not how we're going to do it. So how are we going to do it in our batch text record data processing? We're going to take the middle option on this slide. We're going to take read line. So we're going to read a line, do some processing, write a line. Read a line, do some processing, write a line, until there are no more lines to read. Now it turns out there's a really neat way to read files where it will keep track of how many lines there are. And this is the way that files are like sequences, because we can read lines of a file in a for loop, and it will take care of how many lines are left, just like a for loop will do that in a collection. Sorry, that's a Java word, in a list. All right, let's look. So what did we do here? So this is print file.py, prints the file to the screen. Oh, that's good. So we say in the main we have fname, I guess that's file name, equals input, enter file name. Okay. In file equals open, fname for reading. Data equals in file read. Okay, so that reads everything into a string, Okay, we can see it with data. Then we simply say print data. Okay, well, it looks okay. Let's see how that runs. Okay, so that's called print file, and let's just fire it up. So there's our print file, and let's give it a run. So we're going to run it, and what's the file name? I've already created a file. Well, we have one. It's called my new line example text, right? So we already know what should be in that, right? So let's just do it. My new line example.txt. Enter. There it is. Just came right out of it. It opened it. Okay, let's look at the sorry, I'm looking at the wrong thing. We want to see a print file. Okay, so we prompted for the file name. I knew that I didn't have to put any path expression in front of the file name because I knew my new line in example.txt was right in here in the directory with my programs. So that's the current directory. Didn't have to fool with path expressions. Okay, so then we opened it for reading. We did a read on it that gets everything into a single string called data, and then we printed it. And as we remember, whoosh. Now I'll give you another one. That is the beauty of this is I have one called personnames.txt. person_names.txt. And here are a bunch of person names. Okay, so the fact that we have to open files, open file objects, and associate them with a physical file on the disk drive, that creates the power for us to pick a file that we want. So I didn't have to change the program, but I was able to print a different file. So it's only by being able to open the file and associate it with a particular file name that we get that kind of mix and match capability. That's where the real power comes from. It seems like a pain to have to open files, but then that gives us this we're able to bolt this program to all kinds of input files and all kinds of output files depending upon what our intention is. and that's pretty cool. Now, I said that we usually closed files. Did we close in file? No, we didn't. Now, if we don't explicitly close a file, it will be closed for us at the end of execution. It's good form to explicitly close files, and we'll do that in one of our next examples. Okay. Very good for that. So, read line, by comparison, can be used to read the next line from a file, including the trailing new line character. Now, this is going to be really appealing to us because it's going to be very advantageous for us to be processing the input a line at a time. Again, this classic batch processing pattern is read a line, write a line, read a line, write a line. Read a line, process, write a line. Made a lot of money doing that years ago. Okay, so here's the code. This is it. In file, we want to open some file with R. So some file, hopefully that's a character string that has a proper file name and extension in it. And now for I in range 5, that's going to run 5 times, we're going to say line in file, line equals in file, read line. Okay, so we're going to, and then we're going to print it. Okay, and here's an interesting trick. Remember how we said that there's a new line character at the end? Okay, well, how many new line characters do we need? Okay, every time we do a print, we get a new line character at the end. Okay, do we want to read in something that has a new line character, print that whole thing that includes the new line character, plus add an extra one on from the print statement? No, we don't, because then we're going to be double spacing the lines. Well, how can we not print the last character? Would you remember the substring or the slice? Here's a substring or slice expression that says, okay, start at the beginning, because I don't have, to the left of the colon, I don't have anything, so it starts from the beginning. And where do I want to end? I want to end -1. Okay? So what happens is we print all but the last character of the string. So now we get them without double spacing the output, which is not what we wanted in this case. Now, what would happen if there were only 4 lines in the input? And we said for I in range 5. Now, that's going to try to read 5 lines. What if there are only 4? Kaboom! That's not good. So for doing I in range, having to know how many lines are in a file that really doesn't create a very general solution. So we're going to use another trick of the for loop that's really cool. Okay. So what we can do is we can use a for loop to loop through, and it will treat it pretty much like it's a list. It's pretty neat. So here's what we do. Again, we're using in file, and so we open the file for reading, and then we say for line in file dot read lines. Okay. Then we process each line, and then we say in file close. Okay, so what actually happens here is it opens a file and it sucks in all of the lines and it puts them into a list. And what are we doing? We're processing it in the list. Pretty neat. Okay, So Python treats the file itself as a sequence of lines. Okay, so this is an even better way to do it. So the way we just did it before, okay, that depended on bringing them all into memory. Read lines brings them all into memory and puts them in a list. And then, of course, we were just iterating over the list, okay? Well, we can only use that if it's a relatively modest size file. Could we do it if it had a billion records in it? A billion lines? No, probably not. That probably we would run out of memory and the thing would blow up, okay? Well, okay, is there a way to use this automatic iteration and not have to bring them all into memory, to be able to bring them in one at a time? Yeah, there is, and that's what we get on slide number 91. So we say, so we open the file again as InFile, and then we just say for line in InFile. So line is going to be a string that we get back, and then we're going to process this, and it's going to continue to read lines and execute the body of the loop until it goes back and there aren't any more, in which case it's just going to fall through and go to the next thing, and you see that we did InFile close. Okay? Now, did we have to say InFile close? No, we didn't. It's the polite thing to do. There are certain resources associated with input files that you don't want to waste. So if you're a good practice programmer, every file that you open explicitly and you close them explicitly. Now, let's look at the writing side. That's the other half of what we're going to be doing in this batch processing. So opening a file for writing prepares the file to receive data. If you open an existing file for writing, you wipe out the file's contents. If the main file does not exist, a new one is created. So it doesn't ask you, do you want a file already exists by that name? If you want that, you have to, there is code that we could learn how to do where we could say, is there a file out there by that name? Okay. And they would say, yeah, there is a file out there by that name. And then you could say to the user, are you sure you want to use that name? There's already a file out there. Do you want to override it? Yes or no? And then we'd say yes, and then we'd override it. Or no, then we'd ask them to choose again. But right now, if we use the name of a file that's already there, we clobber it. That's a technical term, clobber. Okay. Now, do we actually write over top of it? No, I think what probably happens is probably we delete the entry in the file directory. So there's still some part of the disk that has that data on it. And then our new file probably goes to another new disk file. And we probably write in a whole new spot. Potentially we could be writing over parts of the old file. But as soon as you write over something, be prepared to never be able to recover it. Okay? Which is why you don't want to accidentally write over files. And how do we do our print? Well, we just say print. How do we write to the out file? Okay? So we use print, so that's going to get us a normal line of text with a new line at the end, right? And that's what we want. And then how do we know that it's not going to go to that standard console out file? Well, because as the second argument, we say file equals out file. And out file was the name of was the variable name that we used. Again, we're using a capital letter to start a variable name, not a good idea. Okay? Because it's a variable name. Variable names should begin with lowercase. Now, batch mode processing. This was what IT was about when I got into IT. We didn't have a lot of online capabilities. We certainly didn't have the web yet. I guess that we were waiting for Al Gore to be born. Although Al Gore may actually be older than me, so I don't think we were waiting for Al Gore to be born. But in batch mode processing is where a program input out and output are done through files. The program is not designed to be interactive. Okay, so it's input, process, output, file to file. Well, we do that with a lot of different things. I mean, you don't really think about it, but there are quite a few processes still that are not interactive. People who are going to be working with files that they get from some kind of a business partner that represent some data from the partner. And they're going to have to maybe convert it to put it in the format that is going to be a proper input for our system. Well, we're going to write a batch mode processing program that's going to read a line from the partner's file as input, reformat the data, write a line out to ours. Okay, so anytime we get something from a partner, anytime we need to move something from one system to another, possibly we might be writing a program that has this batch mode kind of thing. We're going from file to file, but it's just part of the guts of our system. It's not the user contact part of the system, but still it's very important processing. Okay? So here's a use case here. We talked about it earlier in the chapter. We want to create usernames for a whole big group of people. And we want to use the same algorithm that we used before. That's why I had a list of person names before. In this case, though, we don't want to type them in. We want them to come from an input file. Well, this actually makes sense. Let's say that our company acquired a whole new division. And now we've got 3,000 people who we've got to create usernames for. Now, you might say to me, Kevin, if you're going to create 3,000 usernames using the algorithm that we used earlier in the chapter, you're probably going to get some duplicates. So you've got to add duplicate checking. And I would say, yeah, that's probably true, but we're not going to do that because we haven't gotten the tools yet. Okay, but it's that kind of use case. Okay, so this one's called user file, and instead of asking the user to put in usernames to type them in, it asks the users for what file are the names in. That's down here. Okay, and that goes into in-file name. That's not a bad name. I mean, that's using that camel case capitalization, which is fine if you're going to use that consistently. And then the out file name. Then we ask, what file should the usernames go into? Go in. Go into. That's what I say. So now we've got two strings, and we're ready to open the files, because what do? Well, we need the string with the file name. It would have the file path and all that kind of stuff in front of the file name, but I just want to point out that we're only going to be using things in our own project, so we're just going to use the file name and extension in that string. And the in file, we're going to open with mode R for write, the out file with R for read, W for write. Okay, so they're called in file and out file. So we've opened them. Okay, we've associated this internal programming file object with the real physical files out on the disk. Okay, in the case of the out file, we may have clobbered something of that same name. We don't know. We don't have any sophisticated built in here to keep the clobbering from happening. Okay? And now we have a process loop. Typical batch, read one, write one. Okay? Well, this is good. Input, process, output. So we say for line in file. So that's going to get us, every time through the loop, line is going to refer to the newest input line. Okay? And so what are we going to do? Well, there's what's on the record, first and last names separated by a space or more. Okay, so we say, so we already have, because we're going around this loop, and we say for line, we don't have to read. Okay, what it does is it's done a read line for us. Okay, and so we split the line. Now, what's the character we're going to split on? Well, we don't say, so it's going to be a space. And are we going to put those into a list? Well, intermediately, I think they go into a list, but where are they winding up? They're winding up in the variables first and last, so they're each string variables. And now we need to do some processing, right? Well, in a certain way, this is processing. So what's the input? The input is line. So the splitting is processing, okay? Creating the username is processing, so we call it uname. So we're taking the first position of the first name and from the beginning to 7 positions of the last name, and we're going to turn them to lowercase because we'd like to have a standard approach to capitalization in our usernames. So we just call, here we're creating the string with an expression, and then we're calling lower on it to get the lowercase version of that expression, and that's going into uname. Okay, so that's processing. And now output. Okay, write it to the output file. Print uname file equals out file. Do we have to worry about line feeds, new lines? No, we don't have to, because we use the print and we automatically get that. It's part of the services that come from print. How do we know it's not going to the console? Because we said it should go to out file. How do we know what file this file object is associated with, out file? Well, we associated it to a physical file in the operating system when we did the open. So we run around this loop for every input, we create an output. Okay, we have an implicit read up here, and we have an explicit write down here. Okay, so when we come out of the loop, when all the lines of input are gone, then we're done. So what do? We do 2 closes. We do an in-file close because it's the right and polite thing to do. That makes sense. We do an out-file close because we don't want to get screwed. Okay? The computers use a way to both on input and output for files. They use something called buffering, which means that not every time we write a line or we read a line does it go out and get that off of the disk drive. What it tends to do is get a block of them at a time. It might get 10 lines, or it might get 100 lines, depending upon how long they are. And it puts it in a buffer. So every time we do a read, it doesn't have to go out to the disk drive, because that takes a long time to turn that disk drive, because it's a very physical device. So we have what we call buffering on both the input and the output. Now, if in fact we forget to close the input file, we're going to leave a lot. We might be leaving some things in the buffer if they haven't all been read, but we don't care. We're not destroying anything. It's all still out on the physical file. On the output file side, though, it doesn't write everything immediately. Sometimes it will write for, say, maybe you write 10 lines, then it will write a block of 10 lines to the physical disk file. So if you quit the program without closing the file, you run the risk that you might not get the last 4 lines because they get stuck in the buffer. So closing output files is necessary. You're going to lose data if you don't do it. Closing input files is good programming citizenship. Okay, so that's the last thing we do. So we prompt for the file names, and we just go back. We prompted for the file names. We opened the input and the output file. Then we ran around a loop where we got an input line, we processed it, we wrote an output line, and then when we're out of input lines, that's it. There's a one-to-one correspondence between input and output lines, typical batch processing pattern, and then when we're done, we close both of the files. We print some kind of message so that we can see that the program did something nice, and then we're done. So let's just look at this one actually work. The last time we saw this file, it was called personnames.txt. Okay, and how would you create a personnames.txt? Well, it could be created one of two ways. Either some user created it with the text editor. That's what I did here. Or it's output from some other program. So this idea that we would have a series of programs that read one input file, process it, and then create one output file, and then we pipe that into another program, and that's the input file, and then that creates the output file, and then we pipe that into another program. This is a very popular pattern from early IT. In fact, the Unix operating system has this symbol called the pipe, where you can just take a bunch of programs and pipe them together, you are in a very quick way passing things from program to program to program. We're not going to do that in that kind of style. We're going to do explicitly with file names that we're using. So in this case, I created this input with a word process, a text editor. But in the real world, maybe this is the output file from some other program. Okay, so these are the 5 people who we need IDs for. So we've got username.py. It doesn't take a lot of examination to show you that that's the program that we just saw in the slides. Okay, so let's run that. Okay, now where do I want to put it? Well, I already ran it before. How about that? Oh, no, I didn't. I deleted it. So let's run it the first time. Okay, run it the first time. So enter your first... I'm sorry, this is the wrong program. Let's kill that. Terminate it. Okay, so we got that. So we don't want username.py. We want, what is that baby called? Gosh, I'm running out of gas here. It's batch usernames, but what did we call it? User file. Oh, okay. It's the file version of usernames. That makes sense. Okay. Userfile.py. What the instructor really meant to say was this. All right, this makes more sense. So we are prompting for the file names. We're opening the files. Then we've got the input process output loop. We get the input, we do the processing, we do the output. Then we close the input and the output files. We print a little informational things. It's always kind of nice to print something here so that you know that you got through to the end successfully. And then you're done. Okay, so let's give this a run. Maybe this will do something better. And it's going to say, oh, what file are the names in? Well, didn't I put them in names.txt? Okay, good. What files should the usernames go into? And let's put them in usernames.txt. Usernames have been written to usernames.txt. That's good. Okay, let's look for usernames.txt. Well, it's right here in my directory. Because I didn't use any path expressions in front of the file names, everything is right here in the same directory. So if I open that, give that a double click, here we are. You know what? These three work, but I don't. What was in names.txt? I don't know what was in names.txt. Let's look. Oh, that's actually his input. Okay, so his version, John Zelle, Elmer Thudpucker, Guido van Rossum is the father of Python. So then he got usernames.txt. So this is username for Zelle, the one for Thudpucker, the one for Van Rossum. Okay, that's good. All right. Let's say we want to run it again, okay? But instead of using his input, names.txt, let's use my person names.txt. And what's in person names? I'll remind you, some famous people. Some from long ago, some from today. Okay, so I'm expecting to get 5 usernames. Okay, that looks good. So let's save this. Okay, and then let's run the program again. So this is called userfile.py. It's up here. Sorry, if you double click, you go to full. You go to full screen. If you double click again, things go back in the little panels. I don't know if I've ever explicitly said that. Okay, so let's give it a run. Give it a run. Okay, what file are the names in? Well, it's person underscore names.txt. So person underscore names.txt. Okay. And where is it going? Well, let's just put it in usernames.txt. That's going to blow away the last one. Okay, because if you look, usernames.txt, it's fine. It's got the 3 names that John Zelle was interested in. I'm going to blow it to smithereens by saying I want to use the same file names. Usernames.txt. Okay. Well, there are the new values. So actually, it looks like it kept the same file entry, and it just overwrote the data. So Michelle Obama is Mobama. Barack Obama is Bobama. And any username algorithm that gets you both a Mobama and a Bobama for the Obamas, who I'm a big fan of, is got to be a pretty good algorithm. So pretty good indeed. And the username for Linda Sarsour, who is a kind of women's rights, people's rights advocate, who I met in my days in the March on Washington back in the days of the Women's March. She was one of the leaders. It gave her El Sarsour. Oddly enough, that's what she uses as her name in Twitter. She is El Sarsour. So maybe this isn't a bad algorithm at all. Of course, that's all of her last name. So I just showed you what happens when you give a file name, and you can type in anything, and without further checking, you're just going to write right over top of it. Now, let's do a little more testing. What happens if you give it a bad file name? So bad file name dot text. What file should the users go in? Let's say bad file output dot text. Kaboom! Okay. So what happened? Well, no such file or directory, bad file name dot text. What happened? Where were we? Well, let's click on that last link. We were up here trying to open in file. Okay. And it couldn't find it. So it just blew up. Now, could we write some code eventually to look ahead and warn the user about that and not end ungracefully like this? Sure you can. And that's what people do with production quality programs. Now, what about that output file that we had, bad file output? Is that out here? No, that's not out here because we never got that far. We blew up in line 13. We would have created that file out there. It would have been empty, but we would have created it in line 14, but we never got to line 14 because we blew up right here in line 13. Okay, now that's okay for us right now. Again, you can only make your program so robust with the tools that we have so far. Okay, we're pretty close to the end here. Something that is in the assignment for this chapter is to take one program that we did earlier in the chapter where we got a line of input typed in and we manipulated it and we gave a line of an appropriate process line of output, and we did it one line at a time. They want us to convert it to a batch program, which means we've got to follow this kind of model, okay? And the fact is, what do we have in our earlier program? Well, we have just the middle. We probably have something. Probably have something that looks kind of like this code. You know, something like that. That's all we have. So, you know, we're going to have to create the rest of this loop. Okay. And then we're going to have to open and close the files. And also we're going to have to prompt for the names of the files and all that kind of stuff. But this is in the one where you're supposed to create a batch program. This is what you're doing. You're taking a little bit of code from another program and you're finding a way to adapt it to this batch kind of a model. Read a record, do some processing, write a record. Read them and write them. That's it. So I think we're pretty close to the end here. Things to note: it's not unusual for programs to have multiple files open for reading and writing at the same time. Okay, so we can have more than one input file open at the same time, more than one output file open at the same time. What are the restrictions on that? Well, memory. Okay, every time we open a file for either input or output, we use up a lot of memory because I mentioned the buffering. So could we open enough files that we ran out of memory? Yeah, we could. Apart from that, we just have to give them a different names and keep them straight. Okay, and we have to kind of understand what they're for. The lower method is used to convert the names to all lowercase in the event the names are mixed upper and lowercase. So this is a common thing that's done with both usernames and passwords to get around the problem that people forget how they capitalized what they did. So pretty typically when applications store a username or store a password, they will convert it to all lowercase. And that means every time you go to log in, it will take the username and the password that you type in, and before it goes to search for it, it will shift it to lowercase. So then we don't get into trouble with capitalization problems. Probably less, more with usernames and less with passwords, because passwords these days we want capital letters, we want numbers and all that kind of stuff. So not a good strategy for passwords, but great strategy for usernames where people forget whether or not they use capitalization. It's hard enough for them to remember the characters. So that is it. We're done. It's a long chapter. There's a lot in here, though, and now you're able to do a whole lot of things you weren't able to do before. Good luck with the exercises. I'm going to be providing some tutorial examples, and I'll see you then. So bye-bye.